Greetings, geometry students. I appreciate you finding time to do your notes. We're getting into a new unit, and we're going to switch gears considerably. And all of the material we're getting ready to look at over the next several days is going to be related to the non-polygon circle. So let's get started. Our lesson for today is going to be central angles in circles, and our objective will be the student will learn the relationship between a central angle and its circle. Now, while you're getting caught up, let's just have a brief discussion here. Okay, one of the things that separates the circle away from every other shape that we look at in geometry is a term that I've already used, non-polygon. Okay, circles are not polygons. Everything else that we have studied thus far has been. Now, if you remember back to your definition, a polygon is an enclosed figure that is built entirely out of line segments. Well, clearly a circle is not built out of line segments, so we'd probably better have a pretty good understanding of what it actually is constructed out of. Okay, circles are a special shape, okay, obviously, so we expect that they will have special vocabulary to go with them. A lot of the things that we're going to be looking at is going to be new vocabulary, but this vocabulary also, most of it, comes attached with mathematical formulas that describe how that vocabulary applies to the figure. Okay, so we're going to be seeing a lot of new terms, but we're going to start off with the obvious. We're going to see if we can come up with a definition for circle. Now, if you think back to Euclid's The Elements books, okay, you will remember that we started off this year by saying that everything in geometry, in Euclid's geometry, can be broken down into one of three basic structures. They are 0 dimensions and 1 dimension and 2 dimensions. They are the point and the line and the plane. Well, everything we have seen so far this year has been built out of lines. Later on this year, we'll start adding some planes in there and get some three-dimensional objects. Okay, but what exactly is a circle built out of? It's obviously not built out of planes. It's obviously not built out of line segments. So the only thing that remains is a circle must be built out of points, and that is exactly what it is. Okay? The textbook definition for a circle is that it is a set of all points that are equidistant from a given point. Now, we've actually seen this definition earlier this year, but we may not have paid it much attention. Okay, C-Scope looked at it when we were trying to discuss the difference between Euclidean and non-Euclidean geometries. Okay, but a circle is a set of all points that are equidistant from a given point. Well, this uses a bunch of vocabulary that we already know, okay? The key being equidistant, the same distance. So if you begin with a central location or a single location, like at the center of all of those blue rays that are in there, okay, there is a single point that everything emanates from. And if you measure out the same distance infinitely in all directions away from that point and place an infinite number of additional points, these red guys, place them the same measurement away from that central location, eventually those points will cram closer and closer and closer together so that you cannot tell the difference between any of the points. They will basically blur together and make a continuous bent shape, which we call the circle. Okay. Now, obviously, we need a way to name our circle. Okay, as always, we will call our geometric shape by what type of a shape it is. So when we talk about a circle, we will announce it is circle, and then we name it, and the naming system is typically after whatever its central point is named. Okay, so if there's an A at the center of all those blue rays, then we would say that this guy is circle A. Okay, now there are several angles as well as lines that will interact with our circles, so we're going to kind of take them just a few at a time. We'll start off with this one. A central angle is an angle in a circle that has its vertex on the center of the circle and its endpoints on the circle itself. Okay, a diagram that would accompany that definition would look like this guy. Okay, you can see we have an angle in our circle. Its central or center point, its vertex, is positioned on the center of the circle, and the rays, the legs of the angle, extend, and they make contact with the circumference of the circle. Okay, so a statement regarding this situation might read something like angle ABC is a central angle of circle B. Now, quite obviously, our central angles intersect our circle at two places. Okay. These two places on our circle kind of provide endpoints for what we refer to as an arc. Okay, so those 2 points are the endpoints of an arc on the circle. Once again, using the same diagram again, you don't need to copy it again, but another statement that could be made about what this central angle did to the circle is arc AC is an arc of circle B. Please notice that we have a new notation over our A and our C. Okay, looks like a little rainbow over the top. Some people call it a toenail clipping, whatever. Okay, but over the top of our AC, you have a little bent guy. It looks like a rainbow. He is our shorthand or symbolic notation for arc. Okay, so you can add that notation to the notations we already have, like line segments and rays and lines. Now, there is a relationship between the central angle in the circle and the what we call intercepted arc. That is arc AC that you're looking at right there. It is the part of the circumference that is caught between the legs of the central angle. So let's look at that relationship. The connection between a central angle and its intercepted arc is, and the relationship here is that the measure of the angle is going to be equal to the measurement of the arc. Now, we haven't talked much about circumferences or anything like that this year. We'll get into a discussion of that later on this year. Okay, but circumferences are measured in degrees as well. They are measured in other ways. Okay, it's not degrees isn't the only way to do it, but the way we're going to be talking about in geometry is by degrees. Okay, so using this same diagram, you don't have to copy it down again. Okay, but a statement that could be made about the measurements of the angle and the intercepted arc in there are that the measure of angle ABC is going to be equal to the measure of arc AC. And I've already let the cat out of the bag on this statement. Both are measured in degrees. And again, we've already talked about it this year. Degrees are not the only ways to measure angles, and now we're saying they're not the only ways to measure arcs either, but that is the only method we're going to be looking at in geometry. Now, another side note here is that arcs come in many sizes. Obviously, as the angle changes, the angle size changes, that's going to change the arc size. Okay. Those sizes place those arcs into one of two categories. We have what we call minor arcs, and we have what we call major arcs. Now, a minor arc, basically, in plain English, would cover less than half of the circumference of the circle. So a minor arc would measure up to 180 degrees, but it would not measure 180. A major arc, on the other hand, would cover more than half of the circle. So a major arc would cover anywhere from 180 degrees up to 360 degrees. But again, it would not cover exactly 180 degrees. If an arc actually did cover exactly half of a circle and measure exactly 180 degrees, well, you probably already know the term for that, and that term is semicircle. So if an arc were to measure exactly 180, it would become a semicircle. Okay, so in summary, minor arcs are from 0 up to 179.99999. Semicircle is exactly 180, and then a major arc would be 180.000000001, and then up to the 360 degrees of being the entire circle. Okay, now there's a procedure for naming the arcs, and there's a little bit of a catch to it, so let's talk about it. When naming arcs, it is only necessary to use 2 points for minor arcs. Those would be the endpoints, just like if we were talking about a line segment. It begins here, it ends there. We identify those 2 marks. Okay, but if you are talking about a major arc, it's going to take 3 points to name them. Now, the first point that you list and the last point that you list, those are still going to be the end points, but we need a third point for a major arc to actually force that measurement to go the long way around the circle. For example, look at this diagram, copy it down. There's angle, central angle ABC still in there. And we can see that we have arc AC that we have been talking about. Would arc AC be minor or major? Arc AC would be minor, okay, because it covers less than half of the circle. Now, if you're wondering, hey, wait a minute, couldn't you start at point A and go counterclockwise all the way around the circle to get to point C, and that would make it a major arc? Okay, true enough, that would. Okay, but the naming of arcs, just think of it like this. Think of it like it's lazy. If you gave the circle a choice to go between point A and point C along the circumference, if it was lazy, would it choose to go all the way around, or would it choose to take the shortcut and just go clockwise to get from point A to point C? Well, it's going to be lazy. It's going to go the short distance. That's why AC is automatically a minor arc, and that's also why we only took 2 points to name it. If we want to go the long way around the arc from point A to point C, then we have to include an intermediate point like point D to force that arc to go the long way, to tell it that it cannot be lazy and cut the corner between point A and point C along the circumference. You're going to have to go from A all the way around to D and then around to C. That's why ADC is a major arc. Okay, so you ought to be able to just look at the names, okay, of an arc in order to decide if it is a minor arc or a major arc. Two just endpoints for a minor, okay, endpoints and an intermediate point for a major arc. Now some little basic math here. Arcs can be added together in order to form larger arcs by the arc addition postulate. Okay, we talked about a very similar postulate to this one earlier this year. Okay, and remember, a postulate is just a fancy word that means it's kind of common sense. This is saying you can take 2 small arcs, you can add them together to end up with a larger arc. Okay, same thing would be true with subtracting. You could take a big arc, take a small piece away from it, and you would end up with a smaller arc. Kind of common sense, but it is a rule, so there it is. And similar vocabulary, just to reaffirm what we already know. Okay, if 2 arcs have the same measurement, then they are called congruent arcs. So the term congruent continues to apply for us inside of circles. All right, I think you get the basic idea here. What I want you to do is I want you to copy down this diagram. I have 5 what I think are very simple questions to go along with it, and I would like you to give these questions a try before arriving in class with these notes. Okay. So take a look at circle A. Circle A obviously has several radii drawn inside of them, or inside of it, and there are various measurements at the central angles inside of circle A. Okay, so copy down circle A, and then I'm going to give you these questions. I will leave the video running here for about 60 seconds so you can copy down the questions, but the audio is about to end. I appreciate you taking time to get your notes done, copy these down, answer them, and I'll see you in class.